And on that note, I will introduce our next speaker, Mindaugas Potapovas. I hope I pronounced that Greek enough. Mindaugas comes to us from the University of Vilnius, where he is doing his PhD studies in biophysics at the, I wrote that down, in the Vilnius University Life Sciences Center, Institute of Biosciences at the Department of Neurobiology and Biophysics, Brain States Research Group. And he specializes in EEG, neurobiology and chemistry, where he's looking at auditory steady states and biomarkers for response to psychedelics. And today he will tell us about how Psilocin and a serotonin blocker affect brain responses to sound in rats. Maybe we can learn something from that on translational implications for humans and how we react to sound, and that is quite interesting because a lot of psychedelics are used in musical settings, and music is almost always present in psychedelic research and therapy. So please give him a warm round of applause.
Okay, so yeah, as I was introduced now, I'm coming from Vilnius, Vilnius University, to be in particular Life Sciences Center. And the work that I'm going to present is actually not only my own, but there are several people involved with this. So I also would like to thank Česmír Vejmola. He was mentioned here before. He was also working with animal models and EEG. He's from National Institute of Mental Health, also from Charles University, especially Third Faculty of Medicine, as well as my supervisor, Inga Greškova-Bulanova, and Evaldas Pipines, that are also from Vilnius University, and also Tomáš Paleneček from National Institute of Mental Health. So, the topic is about brain responses and how we are measuring brain responses, actually now in rats, but it can be done in humans. And this is about auditory steady-state responses. This is a biomarker or just a tool that I use daily to probe into what kind of signals we get from the EEG and how we can analyze that. And here you can see that, for example, we are using a periodic stimulation, and this periodic stimulation can be, let's say, 40 hertz. And here, every single spike that you hear is a different sound, and this sound can be seen in the EEG response then as a periodical wave corresponding to the same frequency that we stimulated the brain with external auditory stimulation. And then later on, you can analyze that in the frequency and the time dimensions. And this plot is called time-frequency plot. And so the stimulation, the response, and then the analysis of response, it corresponds exactly. And this, the different shading, the different colors of it, it signalizes the strength of the response that we got. And, well, some other things that it is used in sensory processing, cortical synchrony, and network integrity. And also, as I mentioned before, it's used quite... it's actually used already in clinical and preclinical neuroscience. Okay, so moving forward, but why 40 hertz? So the most essential thing about 40 hertz, that 40 hertz in EEG context is known as gamma brainwaves. Gamma brainwaves can be differentiated into lower ends, like from 30 to 50 hertz, and also higher ends, so from 50 and up to 100 hertz. But why 40? So 40 actually corresponds, and it is known that it is about inhibitory excitatory balance. And here we have a Grant and Young by colleagues of 2023, and they proposed a quite known already model which corresponds to the cortical circuits of neurons. And we have pyramidal neurons, and we also have parvalbumin interneurons. So the parvalbumin interneurons are inhibitory, and the pyramidal neurons are excitatory. And then we have, as it is signed out here, that from pyramidal neurons, we get inputs through AMPA and MDA receptors to the parvalbumin neurons. And as they are being excitatory, so they are exciting the parvalbumin interneurons, and then those on their own are trying to reduce the excitation of pyramidal neurons. As you can see here, it goes, and then we have GABAergic, which is a modulatory molecule, which is reducing the action potential probability in pyramidal neurons. So this, what I just said, is known as inhibitory excitatory balance. That's why we're using 40 Hertz. And also it is known that it is impaired in psychiatric conditions, for example, schizophrenia, bipolar disorder. It can also be modulated by psychoactive substances. And one of the most recent and interesting things that I found out is that it is a direct resonance, or can be considered as a direct resonance, though it is very early, of cytoskeletal frequency. So the microtubules are also resonating, and it can be directly correlating with the 30 Hertz also as a signature of consciousness, but not about this today. So why study psychedelics and serotonin? So another article that I use here, so from Zhang 2024, they say that, for example, psilocin, when it acts on glutamatergic neuron, and they have the 5-HT2A receptor, which was already mentioned here today, then the action potentials actually of the glutamatergic neuron are increased because 5-HTA, as I say here, 5-H2A receptor is depolarizing neurons. From someone who already have some background in neuroscience know that there is a possibility or more likelihood of more action potential. So it means that the pyramidal neurons will fire more. But if we are also acting off 1A receptors, which is known that psilocin is actually working on those two, so they hyperpolarize them, then there are less of action potential. So it's excitation, inhibition, balance again. But it's not that linear. And it was also mentioned here today that it corresponds to neuroplasticity. So this is the basic receptor level work of how its action is translated inside the neurons. So what our research questions today will be, quickly, that we're interested in how psilocin affect 40 Hertz phase locking index in auditory cortexes, also affect dose dependent, because we use 1 milligram and 4 milligram of psilocin in rats, and also does blocking the 2A receptor with MDL, mimic or oppose psilocin. MDL is an antagonist, and also are effects hemispherically lateralized, so left versus right, because it is known up to date that when we are measuring auditory steady-state responses, we can see a certain predisposition of right auditory cortex to respond strongly, more strongly. So what we did here was that we had 9 long-given rats, male ones, and it was a within-subject crossover design. We had 4 drugs. So as I mentioned before, saline, psilocin, MDL. Psilocin had 1 and 4 milligram per kilogram concentrations. And then we performed an auditory stimulation paradigm. So it was 40 Hertz, 1 second click trains, 120 times, and 30 minutes after drug application. And then we measured EEG. We measured EEG and A3, which is left, and 4. Actually, we measured 40 electrodes, and this is the showing of the map where they were placed on. And then we decided to analyze A3 and A4 because these had the strongest response, because they are the temporal and or auditory regions. And we also analyzed the intertrial phase coherence, so it's from 35 to 45 Hertz and the baseline and so on. So again, a little bit about what is intertrial phase coherence. So the major note that you have to take out of this is that the higher ITPC is, the stronger neural entrainment is, and the lower ITPC or the intertrial phase coherence is, the more disruptive phase coherence, and the more out of sync the whole brain structure might be. Okay, so, and now we are having our, again, as I mentioned before, we have time frequency plots, and here you can see there's saline, 1 milligram per kilogram psilocin, and first, what we noticed that was a hemispheric difference. So only A4 side, which is right cortex, responded to the injections of the drugs that we used in rats in this study. Why it happened? I'm hypothesizing because maybe because they were constrained, they're not freely moving, they had some compensatory mechanism, and the right side might be more even serotonergic susceptible. And here is again, we have just time courses as well. This is left side, this is right side, and you can see there is a difference and there is almost none difference. So again, we just see that the only significant effects that we saw was in the right cortex. And then moving a bit deeper into the effects of what we've seen in the right cortex. So we've seen that the MDL, or antagonist of the receptor, it increased compared to saline and psilocin, the intertrial phase coherence, and 1 milligram per kilogram. It had a trend towards increasement, but it was not statistically significant after the corrections. And so this suggests, the main idea from this is that this suggests that there is an inverted U modulation pattern. So the less psilocin you have, it might actually increase the coherence of the brain, but the dosage, if you're increasing it, this desynchronization starts to happen more rapidly. And MDL, as being an antagonist, so it acts completely different, like the opposite of action of psilocin, then it gives a response which is expected. And this is the individual differences, so the saline, then the increasement that we saw in the 1 milligram, then decreasement actually of 4 milligrams. So the individual rats actually have, some of them had desynchronization of cortical activity, and MDL also the increasement that we've seen before. So the mechanistic interpretation for it, would be that we have at the low dose psilocin, it's actually potentially enhancing GABAergic interneuron synchrony, and then we have the higher ITPC levels. Then the high dose psilocin actually probably is related with the desynchronization, which we see as a flattening of the response. The MDL, being an antagonist of the same receptors family, is exciting and inducing interneuron-driven gamma rhythms to stabilize. As I mentioned before, it is probably related with the U-shaped inverted effect curve, and right hemisphere effect, as I mentioned before, was stronger, and at A3, which is the left side, we didn't see any of the effect. So what might be the implications, and why we are doing this in the first place? So 40 Hertz might be a useful biomarker for scanning the brain, not only in animals, but also in humans. And it might reflect excitation-inhibition balance in real time, because we are measuring EEG in real time under the influence of the drug. The phase coherence, so from trial to trial, from sound to sound, is it shows timing precision, not just signal strength, because the strength is just the amplitude, so you can have another measure, but this is about how the amplitudes are corresponding from trial to trial. As I mentioned before, ASSRs can be a translational tool across species. Dosing is important because you see, we have an unexpected effect of 1 milligram increasing the cortical activity, the cortical synchronization actually, while the majority of the studies before say that it just desynchronizes and increases the brain entropy level. And also it supports a critical target that by regulating this 2A receptor, we are doing something with our sensory perception. And so once again, I would like to thank you for my team that is working together on this project. And this is my supervisor, Inga Grishkova-Bulanova from Vilnius University. This is Vilnius University, where I'm coming from, the Life Sciences Center. Česmir Veimola, Evaldas Pipinis, and also this is the photo of National Institute of Mental Health, and Tomáš Peleniček. So thank you once again, and thank you for your attention. Any questions?
I was just wondering if why ECOG wasn't, like why EEG and not ECOG, for example?
That's a good question. In the literature that I read already, a lot of different articles that use auditory steady-state responses, and even others that are doing animal research with EEG, it seems that they cannot decide themselves how to call it. EEG, ECOG, though there is another local field potential when they are actually inserting electrodes quite deeply into the matter, then they are calling it local field potential. So this can be called ECOG, or it can be called EEG. But then if you are calling it ECOG, then you have to differentiate between subdural, which is I don't remember. It's epidural and subdural. So I don't remember which one is actually the deeper one and the outer layer, but it wouldn't be a mistake.
So, higher dose of psilocybin. And I'm going to make a bulk generalization, maybe simplifying things. But in theory, we want the low, let's say, entropic conditions like depression, OCD, addiction, everything that has these rigid patterns and so on and so forth, for the psychedelics to break the patterns, to break the loops, to increase the entropy, to give us the chance for reprogramming. Whereas in schizophrenia, we kind of have the opposites. Mm-hmm. And we have this unpredictability, this chaotic, let's say, condition, already increased entropy, and this might be the reason why we cannot yet pair psychedelic therapy to this kind of disorders. And so you're mentioning the 40 hertz and the excitatory inhibitory balance that is kind of out of order in these disorders like schizophrenia. And so I kind of had the idea, is it implied from your experiments and this U-shape curve that maybe a little bit of psychedelics, a little bit of psilocybin and not overdoing it like with other disorders could potentially restore this kind of balance in these low entropic disorder, high entropic disorders, let's say? Yeah, I know it's oversimplified and generalized.
Definitely not. Your question is actually very complex. And it would be easier to answer from me saying that it's an oversimplification, but you very, very cleverly noticed that, yes, schizophrenic patients and depressive patients, they usually have reduced also the intertrial phase coherence, which means that the entropy is already high, and it corresponds with and actually this psilocin to be used, and it can be called the state that you cause by psilocin, it can be called serotonergic psychosis, which not equals schizophrenic patient condition, but it can be a resemblance of that. But what it does for example, a depressive patient, it, at least what we know so far, desynchronizes the brain, and then the brain it's coming back while the drug is waning off into some kind of a state where it's more structured. The entropy is actually lower than the start.
But my point was in your U-shaped curve regarding the dosing.
Yes.
This was a bit strange for me.
It's also strange for me, but I presented it. I don't know what it means actually. We have to do more research about it. But yeah, it says that like here we have the dosage of 1 milligram per kilogram, and it corresponds to the inverted U shape. Of course, it's not a perfect fit because we have to have much more data, but it shouldn't be here if psilocin would be acting linearly. It means that it's not acting linearly, and probably this corresponds to that it's not working on one receptor. It's working on 1A, 2A, and all the rest probably. The more you get into, the more it works on different receptors.
Yeah. Thanks.
We have time for one more question. Okay, well, thank you very much.
Thank you.